Hello everyone. In the last lecture we have discussed about the Taylor's impact test, impact of finite bar. So today we will continue this discussion. So we will discuss about some additional consideration and some additional analysis by Wilkins and Guinan on this Taylor's experiment. So what we have seen earlier is that the Taylor's experiment that will the final shape of the deformed bar may not be exactly what Taylor assumed. So the main differences may be with the real differences of Taylor's analysis with real experiments. Is number one, the deformed part may not be conical, part not conical. We have seen that that may have mushrooming effect, mushroom shape. So basically when a bar is impacted, so the Taylor analysis says that this is a residual, this will be conical, but then this may not be exactly that, and this will may have some mushroom effect, like something like this. Okay. So and the number two is the boundary between the plastically deformed and elastically deformed. Plastically deformed, or sorry, we would say the plastically deformed and undeformed region is not distinct. That means here the early analysis, the Taylor analysis, it says that there is a clear boundary between this plastically deformed and plastically undeformed part, but in the real material, so sometimes this can have some gradual deformation part, so where we cannot actually exactly know where the boundary is, that is the boundary between the plastically deformed and undeformed part. So Wilkins and Guinan in 1973 they have performed a simple analysis, simple mathematical analysis on the Taylor's test. They studied the reduction of L1 by L0 ratio. So the initially the bar impacting the rigid wall is initial length is L0, and the final length, suppose if we are assuming this is a conical shape, the final length is L1. So how this L1 by L0 ratio will reduce, that reduction ratio? They did an analysis and they did experiment on a number of materials, different materials. we will derive their analysis. So, first they verified that first thing they verified is L1 by L0 ratio is independent of L0. So, they have also performed one experiment on this. They have one experiment on 1090 steel. The material, let us say, is 1090 steel, and this L by L0 and the y axis, and then velocity is on the x axis. So, this is the plot looks something like this, and they use different L0 values. Let us say L0 3 different value like 4 centimeter, L0 equal to 2 centimeter, and L0 equal to, let us say, something below 1 centimeter or 0.8 centimeter. So, they have got all the points for all the 3 samples. So, that means that L1 by L0, that ratio is independent of L. So, they have these points follow this curve, and so what they derive, first we will start with the change in length with time is the instantaneous velocity u. So, the minus sign because it is decreasing length, and then they applied the Newton's second law. So, Newton's second law, that force equal to mass into acceleration. The force on that impacted bar is nothing but the sigma yd, the stress, multiplied by the area. So, area is the cross sectional area of the bar, and sigma yd is the, as we know, dynamic yield stress, and we know that the stress in the plastically deformed area will be sigma yield, that will be constant throughout, and so sigma yd multiplied by u will give us the force. Mass will be rho naught, we have the density of the material, that projectile bar, multiplied by L into cross sectional area. So, this will give us L multiplied by A is the volume, and with density it will give the mass. So, this is mass, and acceleration is du by dt, and this is actually d acceleration. We have a negative sign here. So, because it will the velocity is reducing. So, from here we can cancel out this area term, and then sigma yd will be equal to minus rho naught L du. So, from this expression we can, if we combine it here, so 1 by dt, so we can write as u by dl. So, from A, so this we can rearrange as d by L rho naught sigma yd du. So, if we take the now integration from L0 to L1 dl by L. So, this is from initial length to the final length, and here we have rho naught sigma yd, which are constant out of the integration sign. It will be the velocity will change from u to 0, u du. This will look like ln L this is limit L naught to L1 rho naught sigma yd u square by 2 u so is 0. So then what we will get is ln L1 by L and equal to rho naught sigma yd. We have a minus here, if we this will be minus, so this will give us finally ln L1 by L is equal to minus rho naught sigma yd u square by we can write a 2 here. So this is the expression, and it shows the dependence of L1 L2 with rho u square sigma yd, which is also similarly we got it for the Taylor's analysis. There was some relation for Taylor analysis also, we worked on that. So this is similar. So now that the Wilkins and Guinan they have a correction on this. So correction is they observe that this the thickness of the plastically deformed zone. So plastically deformed zone means we have this rigid wall. So we have, let's assuming it as a conical. So plastically deformed zone, the thickness is actually independent of velocity. So what happens when it hits first, and then that h will increase, and then finally it's got a fixed value of h, and this h is independent of velocity u, that's this impact velocity u, and proportional to L naught, the initial length, or we can write h by L equal to constant. They defined a new boundary conditions here, that means this boundary between these two, and that's as you know that will move to a fixed position, the h will move to a fixed position after the deformation from the earlier relation. So this ln L, so if we want to get this h naught by L out, because h naught doesn't depend on u, and then our earlier relation what we showed is that is a function of u, u square, L1 by L is a u square. So what they did is they have that h naught part, or h naught by L equal to constant, that part out of this relation. So for that they have the limit L naught minus h to L1 h is equal to rho naught u square twice sigma yd u to 0. So this will give us ln L1 minus h, L naught minus h, this is rho naught u square twice sigma yd. So what we can do in the left hand side, little rearrangement, we can do it like L naught minus h, this, and then this will be let's say the right hand side will remain same, and then this will be ln L1 minus L0, this ratio, and H minus L0, and then this will be same L0 minus H. So finally what we can do is we can keep this out, L0 minus L0, H minus L0, will give us this exponential minus rho naught u square twice sigma yd, and then finally we want to get a relation L1 by L0, which is 1 minus h by L0. I am not writing the intermediate steps here, so directly you can find it out, twice sigma yd plus h by L0. That h by L0 will come here, and this if we invert it L0 by L0 minus h, this will give this term. And so this is the expression where the h by L0 term is, you can see h by L0 term, this one term here and then one term here. So they plotted that L1 by L0, they plotted it with rho naught u square twice sigma y by this term, and then found an interesting result for different materials. So as we have an intercept here, and as we know this in the earlier expression, so we have h by L0 term on this side. They verified it for 3 materials: aluminum, steel, and tantalum. So they have did all the experiments, and they got that for all the 3 materials they have these experimental results lie on very close to this line. So that's an important contribution from Wilkins and Guinan, because first they verified that L1 by L0 ratio is independent of L0, and the secondly they showed that H, the thickness of the plastic zone, is independent of the velocity of impact, and that H naught depends only on the initial length L0. H by L0 is equal to a constant, and by doing that they showed an interesting result here, that aluminum, steel, and tantalum shows the same trend. That is, if we plot it L1 by L0 versus this term, that is u square term with the constant rho naught divided by twice sigma yd. So with that so we will we are finishing this analysis part, and then we will have some problems on this and the plastic wave propagation. So first problem we will work on is on von Karman and Dewey's test. That if you remember that the wire, the plastic deformation of the semi infinite wire. So in this test, let's say example, these examples you can find it in from the Mark Mayer's book. So these are solved examples we will work on here. This is let's say we have a material copper wire, and we are given a stress strain curve of copper. The common stress strain curve for this is copper. So now to find from here is determine the maximum strain and the stress. So stress the maximum strain will as we know, we write it as epsilon 1, here it's a sigma 1, and we need to get the plastic wave velocity. Which we denote as C1, C naught is for elastic wave velocity. So these three we need to find out as a function of V naught, the impact velocity V naught. So that's sorry, V1, the impact velocity of the drop weight. So we need to find in terms of that, and that is one common do is we'll write small v von Karman and do is experiment, wire experiment, that is semi-infinite wire or plastic deformation. So we have the stress strain curve. So from there we need to know that as we know that the plastically deformed part, we have a relationship k epsilon to the power n. So what we can do is in the logarithmic scale we can plot that, and that will be like log the natural logarithm of sigma, that will be again log k plus n log epsilon, and this we can plot it, we will plot it here. So log natural logarithm of strain epsilon and log of sigma. So this will look something like this. So here there will be this line is nothing but what we showed earlier. This log sigma is equal to log k plus n log epsilon. So n is the slope and this part is the intercept here. We need to get the properties also, although I did not mention that in the earlier slide. So these properties will be because we know the stress strain curve, then we can get the properties. So these properties are the k value will be 346 10 to the power 6. This will be in Newton per meter square, and then we have the n, the hardening exponent is 0.33, and we have our density, it's copper 8900 kg per meter cube, and then Young's modulus of copper is 129.7 gigapascal. So similarly, so what we wanted to know is the maximum strain. So maximum strain, and we know that the maximum stress will stress is related to it is related to the necking instability. So for necking instability we found out that the maximum strain is equal to n, and that is 0.33. So we will use this, and so what we can have is the C1 is the plastic wave velocity. So we need to find C1 and C0. So plastic wave velocity is d sigma d epsilon divided by rho naught. Oh, okay, we will write rho naught as the density. So which will be from this expression, earlier expression, sigma equal to k epsilon to the power n. So this will be k n epsilon to the power n minus 1, the derivative of sigma with respect to epsilon, and this will be divided by rho naught. So if you calculate, so we have k here, this we have k, we have n, and we have epsilon, actually epsilon 1, the maximum we can take that equal to n hardening coefficient, because this is at necking, the maximum strain corresponds to the necking instability. So this will, if we do these all calculations, this will give us 164.1 meter per second. So that's the plastic wave velocity. And what about elastic wave velocity? Elastic wave velocity is C naught, and as you know, this is simple E by rho naught, which will give us 3812 meter per second. As we know, it's much faster than the plastic wave. So this is actually for, as you know, these are true for slender bar or cylinder, not for unbounded medium. So this is the maximum like plastic wave velocity. So 164.1 meter per second, which is corresponds to necking. So if it is the plastic wave velocity is above that, so the wire will break. Wire will not withstand more deformation, more plastic deformation. So now our first part is the maximum strain. We need to find maximum strain, and then sigma 1 and then C1, all in terms of function of V1, which is the impact velocity. So first part, so what we need to do is epsilon 1, which we have from our earlier equation that we already derived. So that I am not going to write differently. So this directly we are putting this rho naught v square v1 square. This is n plus 1 square 4 by kn to the power 1 plus 1 1 by n plus 1. So this here we know the density, we know the n, which is 0.33, we know k here, and so we need to get the maximum strain in terms of the V1, the impact velocity. So if we calculate, I am not writing all the steps, but it will be 4.4 to 10 to the power minus 4 V1 square. So that's what sorry, this is 1.5 actually. So how you get 1.5 to the power 1, that you can understand. This is square, and this will give us 1 by 1.33. So that will eventually will give you 1.5, because 1 by 1.33 is like 3 by 4, and so this will be 1.5. So this is the first relation. So we will now check the second and third. So for number 2, so we need to find out sigma 1. So sigma 1, as we know, is nothing but this has a relation k epsilon 1 to the power n. So that's how it's now simple. So we know k, we know n, and we have expression for epsilon 1 in terms of as a function of V1. So that will be equal to 27.09, V1 0.5, this one, and the third one we want to get the plastic wave velocity. So plastic wave velocity, which is derivative of sigma with respect to epsilon divided by rho naught whole thing square root when take n and k n epsilon 1 to the power n minus 1 after differentiation. This is rho naught this, and then we have the expression for epsilon 1 in terms of V1, and then I am writing the final expression. So k n to the power 2 minus n minus 1 V1 square n plus 1 square for rho naught to n minus 1. The whole thing we will use the square bracket here instead of this circular bracket. So square bracket n minus 1 twice n plus 1. So yeah, so we got the second relation in terms of sigma, the sigma 1 in terms of V1, and then we got the third relation, the plastic wave velocity in terms of impact velocity. So now we will move forward and we will discuss another problem which is related to the same the example we have shown here. This is example number 2. So for the given material above, like for copper, we need to find the shape of the wave front. So we need to determine the shape of the wave front. Shape of the wavefront at first 0.05 millisecond and 1 millisecond. So after the fall of the weight, so let's say we have the von Karman and Dewey's experiment. The height of the weight was set at height of weight, that means the initial height of the weight is at 1 meter from the extreme end of the wire. So that means the weight will fall 1 meter and then it will hit the wire and the lowermost end of the wire. So we need to first calculate the impact velocity that we can easily find out from this height of the weight where we kept first. So that is nothing but that V1. So this is the solution, we are starting from here. So V1 is nothing but 2gh, h is this one, 1 meter. So this will give us 2 into 9.8 into 1. So this will give us 4.4 meter per second. So that's the impact velocity that weight hitting the wire, lower end of the wire. And now what we need to find is the velocities, plastic wave velocities and elastic wave velocities, so that we can draw the wave profile. So we will now find the plastic wave velocity from the above whatever we discussed in the earlier problem, the plastic wave velocity expression from here. So this will be like kn to the power 2 minus n v1 square n plus 1 square divided by 4 rho naught 2 divided by n minus 1 and to the power n minus 1 to n plus 1. So, here if you see, we know k from the earlier problem we mentioned about k. So, k, we have the value of k, we have the value of n, and then we have the density. So, and we know the impact velocity now. So, earlier we did not know that, but we for this problem we have the impact velocity with us. So, this will give us C1 equal to 660 meter per second. So, 660 meter per second is a very high velocity that we know that wire will not withstand. Why? Because our C1, the maximum C1 that is corresponds to the nicking we found in the earlier problem as C1 is equal to 164.1 meter per second. So, now this problem the wire will break or wire cannot withstand such a high plastic wave velocity. We need to plot the wave profile. So, what we will do is we will assume then C1 as 164.1 meter per second. So, what we got the maximum one, and then we know that C naught is equal to 3812 meter per second that we calculated in the last problem. So, now we need to have the wave profile for two time. First one is for 0.05 millisecond and the second one is time equal to 1 millisecond. So, what we can do is for the wave profile, as we know the x axis will be epsilon and then y axis will be x. So, the wave profile from earlier, if you want to draw, is sorry, this is 0.05 millisecond one, and so this will be like first what we need to do is we will have a C1t. So, C1t time is t equal to 0.05 millisecond. So, this will give as x equal to C1t, which will be equal to this C1 multiplied by t, and that means 164.1 0.1 into 10 to the power minus 3. Sorry, I made a mistake here. 0.1 millisecond, not 1 millisecond. So, this is 0.1 and this is 0.05 millisecond. Okay, that's correct now. So, this is what we need to do is here is 0.05 millisecond, and then similarly here we need to get the x equal to C naught t. C naught t will give us 3812 multiplied by 0.05 10 to the power 3. So, now we can plot that. So, this will something like this, and as we know this value will correspond to this. So, similarly for this, what will be the difference is the distance x, how much it will cover. So, the difference will be, it is at higher time. So, it will be the higher the C naught t. So, we have C naught t. So, let us assume this is T1 and this is T2. So, here C1 T2. So, if you write it clearly, so this will be C naught T2 here, and this is x, and this one will be C1 T2 here I'll let C1 T1, C1 T1. So this will be the wavefront would look taller. As you know, this C0 T2 will be twice as high as this one. So that's the difference here. We have one more problem on Taylor's analysis. So let's say we have the example number 3. So this is on Taylor's analysis. The Taylor's analysis is, as we know, the Taylor's analysis assuming a conical shape of this deformed bar. So we have a copper material, and the initial length of the bar when it hits the target, that bar was the initial length L0. L0 is 10 centimeter, with D0, the diameter of the bar, is 3 centimeter, and we have a velocity of this bar. Velocity when hitting is two velocities. Let's say we are assume 150 meter per second. Let's say this u is 150 meter per second, and we write u1, and u2 will be 400 meter per second. So there are two velocities, and then assume that yield stress is equal to 100 megapascal. Dynamic yield stress is 100 megapascal. So determine the final shape of the bar. So what we can do first is we need to get this term out. So this sigma yd, so that will be we know the density is for copper 89, we'll write 30 kg per meter cube, and then u square, first we will take this one u1, and then let's say I will write u1 here, and then sigma yd is 100 megapascal. 100 into 10 to the power 6, we are writing all in SI unit. So this will give a factor 2, and then for the other velocity, so what we can do, this is square, sorry, so 8930, this will be 400 square, 100 into 10 to the power 6, and this will give us a 14.2. So now we know this 14.2 is a very high value, and if you remember the earlier discussion in earlier classes, so we cannot go with this because Taylor's analysis will not be valid for this, and that will not we cannot predict the shape of from this shape from Taylor's analysis. So so we will go with only this value for 2, and then if you remember the one plot between this on x axis rho u square sigma yd, and then in the y axis we may have L1 by L. The L1 is the, as you know, L1 is the final shape, final length, and the L0 is the initial one. So so L1 by L, and then L1 by L, and then another ratio is L1 by L divided by x. So both of these we can plot with this rho u square by sigma yd. So that we found that this curves that we already did it in the earlier lectures. So this curve is L1 minus x divided by L will look like this, and then L1 by L will be something like this. So if you see that figure from the book, so what you can get is, if the value of this term is equal to 2, so you can find the values of this and this. So this is found to be L1 minus, so L1 minus x divided by L is found to be 0.35, and then that is from the plot that you can find it in the book, and that is found as 0.5. So we know the initial L, so that is 10 centimeter. So from there you can find the L1, you can find L1 equal L1, and you can find x. Then we have to find the diameter as well, because so what you can do is you can assume that the volume will be constant. So the volume will be constant, and then we have as you know this this after the impact, this portion we keep this portion as x, and this will be L1 minus x, and total distance is L1. So this is this part is L1 minus x. So now if the volume is constant, suppose the initial volume is the and the final volume is constant, so what we can do is the initial, as you know, this is only the initial will be as L, and d naught, we will write d naught, and this is let's say the initial is, I will write L and d naught. Pi d naught square L is equal to pi d naught square by 4 x. So you can do the calculations by yourself, just I am that is even given in the book. So this will be L minus x multiplied by d naught square by 4 plus d naught d1 by 4 plus d1 square, which is d1 is the final one, d1 square by 4. So with this we can find the diameter, so and then we can get the final shape L1 x and the diameter, so final diameter. So that's all for today. So that's actually end of the plastic wave chapter, and then we will discuss about on the shock waves in the next lecture. Thank you.